For the modal analysis, need the basic knowledge in control system, which is transfer function and Laplace transformation or state space control system. In this lesson, we will use MATLAB simulation, so for sure you need to know a little bit about simulation and MATLAB. The next thing is to know how to linearize the system using MATLAB simulation. I had a video on this, and the next one will be the basic knowledge in your field to modelize your system. Otherwise, you cannot analyze even the basic analysis of your system. Next, you go to this one. So, in this modal analysis of power system, you should have 3 books. The first one will be power system oscillation. This one is cover nearly everything, but it's a bit hard. Maybe it's a bit hard for you to understand. So I recommend you to use the book on robust control in power system. And another one which you should take a look if you have time to the book on the power system dynamics and stability. So first I will go with the book 1 in the section 3, chapter 3 I think. First you need to know about the first thing, the eigenvectors. This is a bit about math, which I think it's a basic one, but maybe you need to be reminded. So it's about the first one is the right. The thing you need to know is the right eigenvector and the left eigenvector. In modal analysis, you use both, but for basic things, you would use mostly the right eigenvector. That is the definition. And from this, you use it to first thing you have to form your system into the state space form like this, and it should be linear. So first you have to linearize your system and put them into the state space like this. And in the end you have a transfer function from the input U to the output Y. From this you can have the eigenvalue of matrix A. This one will be used in some different cases, but the basic thing you need to know is to calculate the eigenvalue from matrix A. See this from this definition. The next thing is linear system analysis tool in power system. So you should follow this. You see in the book 2. In book 1 they have this, but it's not so clear. So just follow this. So you will have your system, Linux system like this, with why the output of the system is the algebraic variable, which you can remove it later. So it's made in this system is equivalent to this one. Z is just an algebraic variable. So basically we can eliminate Z by U, input U, and the state X. So in the end, you have the same state space in a system. Time invariant, if you normally it should be. And why? From this book, section 3.2. And why you need eigenvalue here? Because the eigenvalue, from the eigenvalue, you can calculate the thing they call it damping ratio. And this damping ratio will decide whether or not you have an oscillation in your system and how big and how long it is. For example, here you have an oscillation with the damping ratio is very small. Normally it should be at least 10%, and in a closed loop it should be 50% or 70%, depends on your design output behavior and so on. Yeah, so here is according to this book, it's at least 5%. And from this, you also, from the eigenvalue, you also can calculate the oscillation of this eigenvalue. So here is just a way to calculate the Modal matrix. So you should follow all this session to understand better. It's the same for lab eigenvalue. And here in the end, why you need the eigenvector? You have this, but how can you map this, the eigenvalue, into this? There should be some connection between this and the eigenvalue here, but how? So that is when you need the transformation from the state to the so-called modal variable. This is the transformation from state to this, because in this model, every state will maybe or maybe not affect other states. So you cannot decide whether a state, the behavior of a state come from which state, and the oscillation come from where, and how many percent of that. For example, state 1 contribute to 50% of this oscillation. But if you look carefully, you have two oscillations. I will zoom it better. You see, one oscillation which is this one, and another one which is this. So the first one will be the frequency from this to this, so it's around 0.002, so its frequency is around 1000. But the second one, we from this to this, so it's in this, from this to this. So it's around 50 hertz. The first one will be 1000, but the second one will be 50 hertz. Okay, so come back to this. So modal analysis is the way to transform a state space system into a cell contains you have the okay, so from this you have a new state, but state space, but in this state is the variable in Z will only affect themselves and have no contribution to another. So for example, we have here a system. It is you have to see the state S1 will affect the state 2, S2 will affect state X1 and vice versa. So from this you cannot say whether or not how many percent of this will contribute to the oscillation and so on, because you have a coupling between the state. So now we have to find a way to introduce a new set of states to set that only that state affect itself and not the other. And here from lab eigenvector, here you have the modal matrix, this one, the normalized, this one. Okay, we will talk about this later, but the important thing, you have a transformation. Now you have a new set of states which only affect itself. So you see the Z1 will affect only Z1 and the same for Z2. So from this you can set, okay, now we have a set of state which only affect themselves itself, but not the other. Okay. The next thing will be the mode. The most, so each eigenvector will be considered a mode because it directly linked to an oscillation with a frequency of oscillation and a damping ratio. And it's just here, it's just a notation. So eigenvector V, which is the right eigenvector, will be called the ETH mode sharp, corresponding to that mode. And so now, how can you say that the which stay in Z and it adds contribute how many percent into this mode of oscillation. So here we just a new notation, just a name. So this one can be related to the ether mode, to the Kate state variable. So you have to some nice equation, this and this, which you come from this book 2. Read it carefully and perhaps do some example inside that book, like this, the one I just showed you here. Yeah, but we'll do it in do another one. It's better. So from this, you have to understand which is the VIK and WKI. So the participation factor will be multiplied between them, and it should be normalized to 1. So from the normalized value, you can say how many percent of this one contribute to the mode. How many percent of the state variable contribute to that mode. So here is an example. So I have matrix A, matrix B, matrix C, and matrix D of a system. I calculate on for the open loop normalized participation factor. So as you can see here, we have 6 mode which have low damping, and 4 modes with have high frequency around 1000. So from this, how can you see this oscillation in your system? The easy thing is to return disturbance in the input. So at the operating point, you plot something like this. So here the operating point is 0. So the input could be 0 actually. So you did a disturbance in a very short time, because you have to ensure that your system will somehow come back to the operating point like this. And from this, you have states at this here. This state 7 and state 8 contribute 25%. 25%. And this one contribute a little bit, not much, but you cannot decide whether the modes come from which one. So you have to do this one, and you will see only this mode, only these 2 states affect, not affect, but exhibit the oscillation here, which is this one. But also, if you see here, this state also contributes some into a lower mode, but it's very small. So this state will mainly affect this one. So normally if you want to dump this oscillation, you have to provide some control effort on the two state. That's a classical way to do. You can have something else, but the main idea is to, if you want to dump these modes, you have to provide the control effort into this state. So perhaps you need some feedback from this state to dump, or you loop sharpen to cut this to dump this out. Okay. And the so that's all for modal analysis.